Okay. So today we're going to be going over related rates, which is a natural topic that we do after reviewing modeling and optimization. So I want you to write down or jot down that related rates is any equation involving two or more variables that are differentiable functions of time, t, and can be used to find an equation that relates the corresponding rates. Okay, so related rates, it relates the corresponding rates. So these types of problems are a little bit like wordier or lengthier than your modeling and optimization problems, but they're very similar too. So for that reason, our procedure is very similar to what we had before. I'm going to actually add like a number 6 down here, and that is state your answer. A lot of times when you have these types of problems to do, and they're for free response problems, you have to state your answer to show that you understand and can interpret what's going on. So what's going on? You need to draw a picture and name the variables and constants. Write down the numerical data with the symbols you chose from step 1. So this is very similar to modeling and optimization. 3, write down the rate that you're asked to find. This is a derivative. 4, write an equation that relates the variables. 5, wouldn't you know, we have to differentiate, but this time with respect to t and evaluate. Okay. So let's check out an easy example first and then a more complex example. I have to say that example 1 I don't particularly see a lot of on the AP exam. Maybe I've seen like one question with it, but it is one to kind of get your feet wet. So it says, assume that the radius r and the height h of a cone are differentiable functions of t. So before I continue reading, or you can continue reading, it's always good to read the problem more than once. I'm just going to start the lesson by drawing my cone, my radius r, and my height h as best as I can. Sorry. They always made it a right angle. And it says, let V be the volume of the cone. So let me write down volume of a cone. So it's 1/3 pi r squared. This is supposed to be a 3, by the way. Times h. And it says to find an equation that relates dv over dt, dr over dt, and dh over dt. Now, it makes sense that you're actually asked this. They're all derivatives with respect to time, and we want a differentiable function of time. I actually didn't mean to cross that out. Sorry. Let me try this again. Better. So all I need to do really is to take the derivative of my equation with respect to t, because I have the variables v, r, and h. So let's do that. So if I take the derivative on the left side of the equation, okay, usually I would just write it's 1, but I'm taking the derivative of v with respect to t. On the right-hand side, 1/3 pi is a constant. So since I see r squared times h, I need to use the product rule. I hopefully fit it in here. So first derivative of the second. So the derivative of h is 1, but I have to write dh over dt because I just took the derivative with respect to t. Derivative of h with respect to t. Plus second derivative of the first. So now if I take the derivative of r squared, I get 2r. Let me use a parentheses here, and I'm going to say dr over dt. I just took the derivative of r with respect to t. So I found an equation that relates all of these variables. Okay, you may want to distribute, kind of polish this up as a final answer, but you're done. So let me know if you have any questions. And you're good to go. Okay, not yet. We have an example 2. But for this problem, you're good. Let me pull up example 2. Okay. Read the whole problem. So as I'm reading it, you can start jotting it down. A hot air balloon rising straight up from a level field is tracked by a rangefinder 500 feet from the liftoff point. At the moment the rangefinder's elevation angle is pi/4, the angle's increasing at a rate of 0.14 radians per minute. How fast is the balloon rising at that moment? So since we're dealing with an angle, I'm going to try to draw this diagram where the angle, pi/4, is drawn from a positive x-axis, because that's naturally what we use in mathematics. So let me fill in some other blanks here. So starting from the beginning, we have a hot air balloon, and it's rising straight up, okay, from a level field. Make a nice green grass there. So that means that it meets at a right angle. And let's say that's the balloon. Okay, and since it's going up, I'm just going to put that arrow there to remind me of that. So now it says there's a rangefinder, and it's 500 feet from the lift-off point, this being the lift-off point. At the moment, the rangefinder's elevation angle is pi/4. So once again, over here, it became pi/4. It was increasing at 0.14 radians per minute. So when we're talking about a rate with an angle, it's usually referencing theta. So we want to say d theta over dt. Okay, radians per minute, and there's radians per minute, 0.14. Let me just write down the units. So now let me finish drawing my triangle, more or less. Please bear with all my drawings. It asks, how fast is the balloon rising at that moment? Okay, so let's go back. The balloon's over here, and we want to know when it's rising. So we know we're going to get a positive answer. When we're drawing something that is vertical, it's referencing y. So we want to say dy over dt is some positive answer. That's what we need to find. So let's get started. We took everything from our problem, drew a diagram, and hopefully everything makes sense. Hopefully you have all your rates written appropriately. That's why notation is so important. There's 2 ways to actually do this problem. Option 1 is like what we went over for option 1 of chain rule, okay? Only because you have 2 things being multiplied. If we have to find dy over dt, that means that we need to have something like this done. Well, we're given d theta over dt, so that means we need dy over dt to find our answer. Okay, so we know this is 0.14. We just need this part right here. If you look at your triangle, sometimes you need Pythagorean theorem, but other times you may just need to know something simple like SOHCAHTOA. Notice that we have this angle, this side, and well, this side is what concerns us. So that's opposite over adjacent. So tangent of theta is equal to it's just the y. This is y. I said it, but I didn't write it. I apologize. You're not going to put a rate in your equation. So we have y over 500. Okay? Now this would be like your x, but we know x is 500. So now if we take the derivative of this equation with respect to theta, then we'll be able to plug this part in. So the derivative on the left-hand side is secant squared of theta, and we just took the derivative with respect to theta. On this side, we have the constant of 1 over 500, and the derivative of y is 1, but we just took the derivative of y with respect to theta. So now, if we multiply both sides by 500, and we plug in our angle measure, because remember, we always substitute at the ends. We know theta to be pi over 4. We can get our answer. So let's think about it. Secant squared of pi over 4 is 1 over cosine squared of pi over 4. Cosine of pi over 4 is 1 over radical 2. If we square it, we get 1/2. And if we take its reciprocal, it's 2. So 2 times 500 is 1,000. I'm trying to squeeze that in here. I'm writing it, but it's not appearing. dy over d theta. Okay. So we're going to plug in 1,000 here. And we find dy over d theta to be 140. And this would be in feet per minute because the distance was measured in feet. And as you can see, your rate was in minutes. Okay? So this is option 1. Now I'm going to go over option 2 with you. So option 2, once again, we have our angle, theta, we have x, we have y, we have 500. We need to find dy over dt, and we're given d theta over dt. This equation would help us because that deals with all the information in this problem and it's based off a right triangle. So in option 2, I'm going to do something similar we did in option 1. We're going to take the derivative of both sides, but with respect to t. So if I take the derivative on the left side of the equation with respect to t, I have to write d theta over dt. If I take the derivative on the right side of the equation, I have to write the dy over dt. Okay? Now, I'm trying to find dy over dt, so if I multiply both sides by 500, I have this expression here. So at that point, just like always, we always substitute our values at the end. So theta was pi over 4. D theta over dt, let me put parentheses around everything, is 0.14. And this is going to help us find dy over dt. So dy over dt is going to be 500 times 2, which we discussed how to evaluate that, times 0.14. So it's 1,000 times 0.14. This is 140 feet per minute. Okay, so sometimes students like option 2, sometimes students like option 1. It is beneficial to know both of them. So now let's state our answer. Okay, so we want to say at that moment, the balloon is rising. I was supposed to say balloon. I don't know what I was writing there. So let's erase that and write balloon is rising at 140 feet per minute. Now, if we were talking before about having a positive answer, sometimes we end up with a negative answer. You should indicate that. But then when you state your answer, somehow say maybe at that moment the whatchamacallit is decreasing at, blah, blah, blah feet per minute. In this case, because it was positive, we accounted for that sign being part of our answer by saying that it is rising. So this is explaining that you know what was going on with this problem, and you should be good to go this time. All right, let me know if you need any help, and good luck.